Good evening, and welcome back to SleepWise. Tonight, we begin beneath the polished surface of the modern world. Beneath the screens and machines, the silent data centers and electric grids, the satellites turning high above the dark, and the guarded systems nations build when they speak of strength, resilience, and independence. Before we drift further, if SleepWise has become part of your evenings, please follow the channel. And if you know someone whose mind stays busy long after the day is done, share this with them too. Despite all the talk about software, intelligence, innovation, and speed, much of modern power still begins in rock. Hidden inside batteries and transmission lines, jet engines and radar systems, reactors and magnets are materials most people rarely think about. Lithium rests inside cells that store energy. Copper carries current across continents and cities. Nickel and cobalt help shape battery performance. Rare earth elements make powerful magnets possible. Uranium fuels reactors for years at a time. Graphite sits quietly inside the anodes of modern batteries. The modern age often seems weightless, almost abstract, yet its most advanced machines are built from stubborn substances drawn from the earth. That is part of what makes critical minerals so fascinating. They are rarely glamorous. They begin not in showrooms or laboratories, but in hard rock, brine, clay, sulfide ore, laterite soils, and ancient geological formations buried far from the places where their final uses are admired. To reach them takes searching, drilling, blasting, hauling, crushing, separation, chemical treatment, heat, patience, and enormous industrial effort. And even then, what comes out of the ground is often only the beginning. A deposit is not the same as a usable product. A mine is not the same as a secure supply chain. So, when nations worry about critical minerals, they are not worrying only about geology. They are worrying about bottlenecks, dependencies, fragile shipping routes, refining concentration, industrial readiness, and the uncomfortable possibility that a highly advanced economy may still depend on a few distant links in a chain it does not fully control. Tonight, we begin with that quiet tension. We begin with the strange truth that the future, for all its elegance, still depends on what can be found underground, what can be lifted, refined, purified, and shaped into the hidden architecture of modern life. And as the world slows, and so do we will follow that journey gently, from national power into mineral dependence, from strategy into geology, from ore bodies and mines into refineries, factories, and the delicate systems that hold everything together. The age may feel digital, but it is still in so many ways mineral. And tonight, we begin there. You can feel it once you begin to look for it. The modern world presents itself in polished surfaces, glass towers, clean screens, aluminum shells, carbon fiber, quiet electric cars, wind turbines turning with graceful certainty against an empty sky. It feels light, frictionless, almost immaterial, as though progress were made of clever code and elegant design alone. But hidden inside that polished world is something older, heavier, and slower. A wind turbine rising over a plain depends on immense quantities of steel and copper, and often on rare earth magnets that help transform motion into electricity. An electric vehicle, so often described in terms of software and range, carries a dense interior chemistry of lithium, nickel, cobalt, manganese, graphite, copper, aluminum, and other materials refined to extraordinary precision. A smartphone, light enough to disappear into a pocket, contains its own miniature geography of the Earth. Traces of silicon, copper, gold, tin, tungsten, rare earths, lithium, cobalt, and graphite, all assembled into something that feels nearly weightless in the hand. Even the invisible world depends on matter. Data centers, those cool and humming cathedrals of the digital age, require transformers, cooling systems, backup power, cabling, semiconductors, concrete, steel, and carefully processed metals. Artificial intelligence may sound abstract, but its infrastructure is physical, electrical, mineral, and vast. The cloud, for all its softness as a metaphor, still rests on power lines, substations, server halls, and materials drawn from very real places. And then there is the strategic world, the world of missiles, aircraft, naval systems, communications networks, satellites, reactors, radar arrays, and the precision machinery on which states rely when the stakes are highest. These systems depend on specialized alloys, conductive metals, magnetic materials, and refined substances that can tolerate heat, stress, corrosion, radiation, and time. The language of defense is often electronic or mechanical, yet underneath it lies chemistry, metallurgy, mining, and supply. This is why critical minerals matter so deeply. When people speak of electrification, they are also speaking of ore grades, processing capacity, and refining chemistry. When they speak of industrial renewal, they are also speaking of permitting, smelting, logistics, and the long distance between a deposit in the ground and a usable component in a factory. When they speak of national resilience, they may be using the language of policy, but the underlying sentence is often about whether essential materials can still be sourced when the world becomes strained. For all our sophistication, civilization remains material. We have not escaped the earth. We have only learned to hide our dependence on it beneath smoother surfaces. And because civilization remains material, nations have begun to look at minerals with a new seriousness. A century ago, strategic strength was described through oil, coal, iron, shipping lanes, and industrial output. Those things still matter, but the map of dependence has grown more intricate. Today, advanced economies also rely on lithium for batteries, graphite for anodes, nickel and cobalt for certain chemistries, rare earths for magnets, copper for electrification, uranium for reactor fleets, and a wider family of materials used in aerospace, electronics, grid infrastructure, and defense systems. The concern is not simply that these materials are useful. It is that some are hard to substitute, slow to develop, technically demanding to refine, and concentrated in particular places or processing chains. A country may have excellent engineers, strong universities, military capability, and industrial ambition. It may design aircraft, build data centers, strengthen power grids, and announce bold plans for clean energy or semiconductor leadership. But if too many essential materials beneath those ambitions must pass through a narrow set of mines, ports, plants, or refineries elsewhere, then independence begins to look conditional. That is what gives the word critical its weight. A mineral becomes critical not merely because it is rare and not because it sounds dramatic. It becomes critical when it is essential to vital sectors, vulnerable to disruption, and difficult to replace quickly. Sometimes the vulnerability lies in geology. Sometimes it lies in processing know-how. Sometimes it lies in environmental permitting, trade restrictions, political friction, or the simple fact that mines and refineries take many years to build. And so, the conversation has widened. Governments speak of supply chain resilience, strategic stockpiles, domestic processing, allied sourcing, recycling, permitting reform, and industrial policy. Companies worry about feedstock, refining contracts, shipping risk, and the long lead times required to secure future supply. Investors study not only demand, but jurisdiction, metallurgy, permitting pathways, water access, energy cost, and community support. Behind every polished discussion of technology sits a quieter question. Who controls the materials and who knows how to turn them into useful form? This does not mean the world is heading toward a simple scramble for treasure. The reality is more patient, more industrial, and more complex. Mineral security is rarely won by discovering one brilliant deposit. It depends on geology, yes, but also on roads, ports, power, chemicals, skilled labor, refining expertise, financing, and trust. It is a chain of competence as much as a chain of supply. That is why this story matters. Modern strength is not only invented, it is also mined, processed, and secured. Once you understand the stakes, the word critical begins to soften into something more precise. It does not mean magical. It does not mean priceless. It does not even always mean geologically scarce. In many cases, a so-called critical mineral may exist in more than one place and in more than one form. What makes it critical is usually a blend of importance, concentration, timing, and difficulty. The material matters to sectors a society cares deeply about, and the path from raw occurrence to refined product is narrow enough that disruption becomes dangerous. That path can be narrow in many ways. Perhaps the mineral is common in the crust, but rarely found in deposits rich enough to mine economically. Perhaps it can be mined in several countries, yet refined in only a few. Perhaps the chemistry is demanding, the waste streams difficult, the permitting slow, the water needs high, the capital cost heavy, or the technical knowledge concentrated in a handful of firms. Perhaps there are substitutes, but they reduce performance or take years to scale. A mineral does not need to be rare in absolute terms to become critical. It only needs to sit at a vulnerable point in a system that people depend on. Copper is a useful example. Copper is not obscure, and humans have worked with it for thousands of years. Yet, in an electrifying world, its role grows larger because conductivity matters everywhere. In grids, motors, transformers, cables, electric vehicles, renewable infrastructure, and data systems. Lithium offers a different lesson. It is critical not because every battery must look the same, but because modern storage has expanded demand for highly purified lithium chemicals at industrial scale. Rare earth elements add another variation. Some are not impossibly rare, but the separation and refining process is technically exacting, and certain magnetic applications are difficult to replicate without them. So criticality is never just one thing. It is a relationship between geology, engineering, time, and dependence. It reflects where minerals are found, how they behave in processing, how quickly new supply can be developed, how much of the value chain sits in one region, and how painful interruption would be for the industries downstream. This is why lists of critical minerals change. Governments revise them as technology evolves, supply chains shift, and strategic priorities move. A mineral that seems peripheral in one decade may become central in the next. Another may remain important, but less exposed as new suppliers emerge or new chemistries spread. The category is therefore practical, not poetic. It is a way of looking at the hidden pressure points of modern industry. And tonight, having begun with the pressure above ground, we can now descend more gently toward the earth itself, toward the places where these materials gather slowly and silently over vast spans of time. Long before a mineral becomes strategic, political, or valuable, it is simply part of the earth. It rests in ancient stone, in fluids moving through fractures, in salt-rich basins left behind by vanished waters, in layered intrusions, sedimentary systems, pegmatites, and volcanic belts. The planet does not distribute useful materials evenly. It concentrates them through heat, pressure, chemistry, and time. And because each mineral forms differently, the geography of critical minerals becomes a hidden atlas, one written not in borders, but in processes. Copper often gathers where hydrothermal fluids once moved through the crust, leaving behind porphyry systems that can support immense mines. Lithium may appear in two very different settings, dissolved in brines beneath salt flats, or locked in hard rock minerals within pegmatites. Nickel can occur in sulfide deposits tied to ancient magmatic events, or in laterite deposits formed through long tropical weathering. Cobalt may arrive as a byproduct of copper or nickel systems. Graphite forms in certain metamorphic environments. Rare earths gather in unusual settings, sometimes linked to carbonatites or ion adsorption clays. Uranium, too, has its own stories, from sandstone-hosted deposits to ancient unconformities and hard rock systems. There is something gentle here. Before politics, before shipping, before refining, there is deep time. Continents shift, magma cools, fluids circulate, mountains rise and wear away, basins fill and dry. Minerals that will one day power vehicles, reactors, magnets, and networks are assembled patiently over millions and sometimes billions of years. Human urgency arrives only at the very end, and yet, where those concentrations formed still matters now. Some countries hold extraordinary copper belts, others sit over rich lithium brines or hard rock spodumene. Some possess nickel laterites, rare earth clays, uranium basins, or graphite belts. But geology alone does not decide the future. A buried ore body is only a possibility. It becomes part of the modern world only if people can discover it, prove it, permit it, finance it, mine it, process it, and move it. That is why maps of mineral wealth are never the same as maps of supply. The earth may provide the concentration, but human systems determine whether it becomes usable. Roads matter. Ports matter. Power matters. Water matters. Skills matter. Metallurgy matters. A deposit may look beautiful on paper and still never become a mine. Or it may appear modest at first, then grow into a cornerstone of an industry because the processing works, the grade holds, and the jurisdiction endures. Tonight, we are still at the threshold. We have seen why these materials matter and why they carry strategic weight. Now we begin to descend toward the geology itself, toward the buried arrangements of matter from which so much of the modern world will later be made. Far beneath the surface, the earth is not still. It moves heat, pressure, fluids, and chemistry through rock over spans of time too vast for memory. Most stone contains traces of useful elements, but traces are not enough. And for a deposit to matter, the planet must do something rarer. Gather what is scattered, enrich what is diffuse, and leave enough of it in one place for human effort to make sense. That is why ore bodies can feel almost miraculous, though they are really the result of patient process. Hot fluids rise through fractures and cool, leaving metals behind. Magma intrudes, separates, and concentrates sulfides. Ancient waters evaporate and trap salts in closed basins. Tropical weather strips some elements away and leaves others enriched near the surface. Sediments accumulate, compress, and change. Metamorphic heat reshapes older material into something newly valuable. A future mine can begin in any of these quiet transformations. long before anyone gives the place a name. Each style of deposit carries its own industrial character. Some are broad and low-grade, asking for immense scale and steady economics. Others are smaller, richer, and technically more complex. Some lie near the surface, open to giant terraced pits. Others hide deep underground, requiring shafts, ventilation, and patience. Some yield one main material, while others produce crucial byproducts along the way. A copper system may also carry molybdenum, gold, or silver. A nickel operation may matter partly because of its cobalt. The supply chains of the modern world often begin with this geological overlap. This is why critical minerals cannot be understood only through lists. A list can tell you what matters, but geology tells you why supply is uneven, why projects take years, and why certain regions become central to certain materials. Two deposits containing the same metal may behave very differently in the mill, the leach circuit, or the furnace, because mineralogy, hardness, impurities, water balance, and energy access all shape whether a resource becomes useful. So, before we return to strategy, it helps to pause here in deep time. A battery, a transmission cable, a turbine magnet, a reactor fuel rod, all begin with geological concentration. The hidden intelligence of the Earth comes first, and human planning follows later. We discover, drill, sample, model, and estimate, but none of that creates the ore body. It only reveals what pressure, chemistry, and time have already written below. That is the first quiet lesson of critical minerals. Modern power may feel fast, but its foundations are ancient. What looks like a future technology story is also a story of vanished oceans, cooling magma, buried brines, altered rock, and mineral grains assembled patiently in darkness. The world slows here, and so do we, as we begin to see that beneath strategic urgency lies something older and calmer, the long geology of concentration itself. Once you begin to read the Earth this way, a hidden atlas starts to appear. Certain regions become legible not just as countries, but as provinces of deep geological fortune. The great copper belts of Chile and Peru, the lithium brines of the Andean salt flats, the hard rock spodumene deposits of Australia, the nickel laterites of Indonesia and the Philippines, the cobalt-rich copper belt of Central Africa, the rare earth systems of China and Australia, the uranium districts of Kazakhstan, Canada, and Australia. Each belongs to its own geological story, written over timescales too large for memory. These clusters are never perfectly neat, but they shape the modern map. A mountain chain may hint at porphyry copper systems born from ancient subduction. A salt flat may conceal lithium-rich brines left by water, evaporation, and basin chemistry. A tropical laterite province may hold nickel enriched by long weathering. An old continental shield may hide uranium or graphite in rocks altered long ago. To an untrained eye, these landscapes may appear empty or remote, yet beneath them lies material that can influence grids, factories, military systems, and industrial policy far away. That is part of what makes critical minerals feel both local and global at once. The deposit itself is always somewhere specific, in a desert basin, a mountain corridor, a forested belt, a dry plateau, a remote outcrop reached by road and drill rig. But the consequences travel outward. A mine in one country may feed a refinery in another, a precursor plant in a third, a battery or magnet factory in a fourth, and finally, appear inside a vehicle, power system, satellite, or defense platform far from where the ore first came out of the ground. Yet, possession of the deposit is not the same as control of the chain. Some countries hold extraordinary mineral endowment but lack infrastructure, capital, energy, water, political stability, or refining capacity. Others hold less in the ground, yet dominate the chemical and metallurgical steps that turn concentrate into usable material. This is why conversations about mineral security move beyond mines so quickly. The true bottleneck may sit in conversion plants, separation circuits, smelters, logistics, or technical know-how built over decades. Still, the geography matters deeply. It shapes trade flows, attracts investment, invites competition, and raises difficult questions about who benefits, who bears environmental cost, and who can promise long-term supply. It also reminds us that the modern world rests on a patchwork of very old places. Deserts bright with salt, rain-soaked tropics weathered into red earth, volcanic arcs, hard ancient shields, and remote terrains where wind crosses stone with no sign of the machinery that may one day arrive. If one mineral sits closest to the heart of the electrified world, it is copper. Copper is not fashionable in the way newer battery materials sometimes seem to be, yet it may be the most quietly indispensable of them all. It carries electricity with remarkable efficiency, resists corrosion, works well in motors, transformers, wiring, substations, and countless industrial systems. It has been trusted for so long that its strategic importance can almost disappear beneath familiarity. But familiarity should not be mistaken for ease. In an electrifying world, copper appears everywhere. It runs through grids and transmission lines. It winds through motors and charging systems. It sits inside electric vehicles, renewable infrastructure, appliances, industrial machinery, data centers, and urban networks that depend on reliable current moving from one place to another. The more a society wants electrification, resilience, and digital infrastructure, the more it leans on copper. And yet, copper does not simply wait in tidy metal sheets beneath the ground. Much of the world's copper comes from porphyry deposits, immense low-grade systems formed around ancient magmatic activity. Vast volumes of rock must be drilled, blasted, hauled, crushed, ground, and processed to recover the metal. In sulfide systems, the ore is often milled into slurry, and valuable minerals are separated by flotation into a concentrate that then travels onward to smelters and refineries. In oxide systems, leaching and solvent extraction may play a larger role, dissolving the copper and drawing it into purer form through chemistry rather than furnace alone. So, even copper, old and well known, is a long industrial story. Grade matters, water matters, energy matters, tailings management matters, community support matters, distance to port matters. A large deposit may look reassuring on paper, but turning it into dependable annual supply requires engineering discipline year after year in landscapes that can be dry, high, remote, and unforgiving. This is also why copper has become newly strategic. As grids expand, renewable power grows, transport electrifies, and data infrastructure deepens. Demand rises against a backdrop of long lead times and declining grades at some mature districts. The issue is not that copper is obscure. It is that copper is foundational. A system can perhaps redesign around some inputs, but it cannot easily imagine an electrified future without immense conductive metal moving through it. For all the modern language of transition and transformation, one of the key materials remains a metal known since antiquity: reddish, conductive, patient, and practical. The future may arrive through dazzling machines, but copper reminds us that beneath those machines lies an old physical truth. To electrify the world is, in no small measure, to keep finding, mining, concentrating, smelting, refining, and drawing more copper from the earth. Lithium tells a very different story. Copper belongs to wires, grids, and continuity. Lithium belongs more to storage, lightness, and electrochemical possibility. It is the quiet metal that helped make rechargeable batteries central to modern life, first in phones and laptops, then in larger systems, electric vehicles, grid storage, backup power, and the growing architecture of an energy system that increasingly wants not only generation, but also flexibility. What makes lithium interesting is not simply what it does, but where it comes from. Some lithium is produced from hard rock deposits, especially spodumene-bearing pegmatites. In those systems, the lithium sits inside minerals formed from the final, volatile-rich stages of cooling magma. The rock is mined, crushed, concentrated, and then processed further, often through energy-intensive conversion steps, before becoming the lithium chemicals used downstream. Other lithium comes from brine, where mineral-rich waters lie beneath salt flats and closed basins, especially in parts of South America. A hard rock mine in Western Australia feels different from a brine operation in the high Andean salars, not only in appearance, but in processing logic, water considerations, time profile, and cost structure. That variety helps explain why lithium supply is not one single chain, but several related chains, each with its own strengths, vulnerabilities, and environmental questions. And refinement is where the story becomes more exacting. Battery makers do not simply need lithium somewhere in the world. They need the right chemical form at the right purity, delivered reliably into a broader industrial network. This is why lithium discussions move quickly from geology into conversion plants, reagents, refining expertise, and qualification standards. A deposit may be promising, but the real test lies in whether it can be turned into battery-grade material consistently and economically. There is also something quietly paradoxical about lithium's image. It is often described as a symbol of the future, yet its production depends on very physical realities. Ponds, crushers, kilns, chemical plants, transport routes, water balances, and years of project development. The battery may appear sleek and sealed, but its origin story is expansive and raw, stretching from desert basin or blasted rock through a long sequence of industrial preparation. That is why lithium became such a central chapter in the critical minerals conversation. Not because it is the only important material, and not because every battery future will look identical, but because lithium came to represent a broader truth. Energy transition is not just about elegant devices and cleaner electrons. It is also about finding the right substances in the right places and learning how to convert them into dependable materials at enormous scale, gently, precisely, and without forgetting the landscapes from which they came. Nickel and cobalt enter the story with a different temperament again. If lithium often symbolizes the rise of battery storage, nickel and cobalt speak more to performance, chemistry, and compromise. They are not present in every battery design to the same degree, and their roles continue to shift as technologies evolve. Still, for many years, they have mattered deeply in high-energy battery chemistries, especially where manufacturers seek a balance between range, stability, durability, and cost. Nickel is especially valued because it can help raise energy density. In simple terms, that means more energy stored for a given weight or volume. But nickel is not a simple material story. It comes from different geological settings, most notably sulfide deposits and laterite deposits, and those two paths can lead to very different mining and processing realities. Cobalt, meanwhile, is often less a standalone mine story than a byproduct story. A significant share of global cobalt supply emerges alongside copper or nickel production, especially in Central Africa. That matters because byproduct supply does not always respond smoothly to cobalt demand on its own. It depends partly on the economics and operating decisions of the primary metal system around it. This gives cobalt a particular strategic sensitivity. A material can be essential to certain chemistries, yet constrained by a supply chain whose logic begins somewhere else. And both materials bring difficult questions. There are questions of processing complexity, emissions intensity, waste handling, energy source, and local environmental burden. There are questions of labor standards, governance, and community impact in parts of the supply chain. There are questions about how quickly alternative chemistries may reduce dependence and how long existing industrial commitments may still require these inputs. Critical minerals are never only technical, they are also ethical and political. That is why battery chemistry is best understood not as a race toward one perfect answer, but as a field of trade-offs. Higher energy density may invite one set of materials. Lower cost or improved supply resilience may favor another. Engineers, miners, refiners, automakers, and governments all meet inside these decisions, each carrying a different objective. What looks like a material choice on paper can ripple backward into tropical ore bodies, acid leach circuits, smelters, ports, and procurement strategies. So nickel and cobalt teach a quiet but important lesson. The battery age is not built from one miracle ingredient. It is built from negotiated combinations. Geological luck, chemical design, industrial capability, and strategic tolerance for risk. Deep beneath the polished promise of modern storage lies a more grounded reality, where red earth, sulfide ore, process chemistry, and national priorities all shape what ends up sealed inside a single cell. Graphite enters the story quietly, yet it sits at the center of a very large system. When people talk about modern batteries, they often focus on lithium, nickel, or cobalt, because those names have become symbols of the transition itself. But inside many lithium-ion batteries, the anode side relies heavily on graphite, a material that rarely captures headlines, yet performs a critical role in how the battery actually works. A battery is not defined only by what releases energy. It is also defined by what hosts and receives that energy as ions move back and forth through the cell. Graphite provides a stable structure that allows lithium ions to enter and leave repeatedly during charging and discharging, which is why the anode material must be consistent, durable, and precisely engineered. The geological origin of graphite is ancient. Natural graphite forms when carbon-rich material is subjected to heat and pressure deep within the crust, often during metamorphic events that reshape older rock over immense spans of time. The result can appear in flake deposits or vein systems, where dark mineral grains are distributed through rock that must later be mined, crushed, and concentrated. Yet the graphite that leaves the mine is rarely ready for a battery. Purity matters, particle size matters, and surface properties matter. Concentrated graphite must often be further purified, shaped into spherical particles, and coated so that it performs reliably in high-performance cells. This is where another branch of the supply chain appears. Synthetic graphite can be produced industrially through high-temperature processing of carbon materials, creating a product with different characteristics and costs. That means the graphite story is not only about mines, but also about furnaces, energy, chemistry, and industrial specialization. The quiet lesson here is that even a seemingly simple material carries hidden complexity. A modern battery does not simply require carbon in general. It requires graphite with very specific characteristics, produced through a chain of mining, purification, shaping, and engineering that stretches far beyond the original deposit. Once you begin to notice this, the battery itself feels different. It becomes less like a mysterious sealed object and more like an assembly of carefully prepared earth materials. Graphite, dark and easily overlooked, becomes part of the quiet foundation that allows energy storage to work as smoothly as it does. Rare earth elements sound mysterious, and perhaps that is why they are so often misunderstood. The name suggests something extremely scarce, yet many rare earth elements are not especially rare in the crust. Their challenge lies elsewhere, because they tend to occur together and must be separated through difficult chemical processes before industry can use them effectively. That separation is what gives rare earths their strategic importance. Certain elements in this family are essential for producing powerful permanent magnets used in electric motors, wind turbines, electronics, and a range of defense technologies. These magnets allow machines to convert electricity and motion efficiently, which is why even small quantities of rare earths can influence the performance of large systems. Geologically, these elements gather in unusual places. Some appear in carbonatite deposits formed through distinctive magmatic processes. Others occur in clay deposits where weathering allows rare earth ions to attach loosely to mineral surfaces, creating a different extraction pathway. At first glance, these deposits may not look dramatic. They might sit beneath quiet hills, forests, or remote landscapes that reveal little about the chemistry hidden below. Yet once mining begins, the real challenge emerges in the processing stage. Rare earth ores usually contain many elements mixed together. Separating them requires long sequences of chemical steps designed to isolate each element with high precision. The differences between these elements can be subtle, which means separation facilities must operate with careful control and considerable expertise. That is why processing capacity matters so much in this sector. A country may possess promising deposits, but without the chemical infrastructure needed to separate and refine the material, the value of those deposits remains incomplete. Mining provides the beginning of the chain, but chemistry provides the key transformation. The result is a supply system that narrows sharply as it moves downstream. A small number of processing hubs can influence global supply, because the most difficult part of the journey lies not in discovering the mineral, but in separating its closely related components. This is the quiet reason rare earths occupy such a distinctive place in discussions of critical minerals. Their value lies less in their mass than in their function, and the world that relies on their magnetic properties depends just as much on chemistry as on geology. Uranium enters the critical minerals story with a different kind of gravity. It is not usually grouped beside battery materials in everyday conversation, yet it holds enormous importance for energy security and long-term electricity generation. Uranium connects geology with one of the most powerful energy systems humanity has ever developed. Like many minerals, uranium appears in several geological settings. It can occur in sandstone deposits, where groundwater once carried dissolved minerals through ancient basins. It can also appear in older rock formations, where geological boundaries created conditions for concentration over deep time. The ore itself is only the first stage of the journey. Once extracted, uranium must pass through milling, conversion, enrichment, and fuel fabrication before it becomes suitable for use in a nuclear reactor. Each stage requires careful engineering, regulatory oversight, and specialized knowledge. This long chain makes uranium unusual among minerals. It is not simply a resource that moves from mine to factory. It belongs to a tightly managed fuel cycle shaped by international agreements, technical safeguards, and decades of institutional experience. The energy density of uranium is extraordinary. A relatively small quantity of nuclear fuel can power a reactor for years, producing large amounts of electricity with very little physical fuel movement compared with fossil energy systems. That property gives nuclear power a distinctive role in discussions of grid reliability and long-term energy planning, yet the same element carries historical weight. Uranium is inseparable from the history of nuclear weapons and the global effort to control their spread. Because of that legacy, uranium supply chains operate within a framework of monitoring, regulation, and diplomatic attention. This dual character makes uranium a unique member of the critical minerals family. It is both a material resource and a symbol of how powerful technologies require careful governance. The ore body in the ground may be ancient, but the institutions surrounding it are products of modern history. When viewed through the lens of energy security, uranium reminds us that critical minerals do not all serve the same purpose. Some materials enable new technologies, while others anchor entire energy systems that can operate steadily for decades. Up to this point, the story has focused on minerals themselves, but now it must move to the mine. A deposit may appear promising in geological studies, yet until it can be reached and worked consistently, it remains only potential. Mining is the process that converts buried concentration into a steady flow of material. The work begins long before excavation, exploration, drilling, geological modeling, environmental studies, engineering design, and community consultation often occupy years before construction begins. Roads must be planned, water sources evaluated, power secured, and permits obtained. Only then does the physical transformation begin. At open-pit mines, enormous drills create patterns of blast holes across exposed rock benches. Explosives fracture the rock, and massive haul trucks carry broken material along spiral roads, descending deeper into the earth. Underground mines follow a different rhythm. Tunnels advance slowly through rock, while ventilation systems move fresh air through the workings. Equipment, ground support, and careful sequencing allow miners to remove ore while maintaining the stability of the surrounding rock. In both cases, the challenge is scale. A modern operation may move tens or even hundreds of thousands of tons of material each day. Only a small fraction of that rock may contain the mineral of interest. This is why mining appears so immense. The valuable element often exists in concentrations measured in percentages or fractions of a percent. To recover it economically, the operation must move enormous volumes of material with steady efficiency. Yet, despite the size of the machinery, the rhythm of a mine can feel almost methodical. Drilling, blasting, hauling, crushing, and transporting repeat in steady cycles. Day and night, shift after shift, the mine gradually converts geological possibility into physical output. But the ore leaving the pit is not yet the final product. It is simply the next step in a longer chain, because the valuable minerals must still be separated from the surrounding rock before they can enter the wider industrial world. Once ore leaves the mine, it enters a stage that is less visible but equally important. This stage is processing, where physical and chemical methods transform raw rock into concentrated material suitable for further refining. It is here that geology meets chemistry. The first step is usually crushing and grinding. Large fragments of ore are broken into smaller pieces, then ground into fine particles, so that individual minerals can be separated from the surrounding rock. Liberation is the goal, because valuable minerals must be exposed before they can be recovered efficiently. Different minerals require different techniques. In sulfide deposits, flotation is often used, where chemical reagents and air bubbles help specific minerals attach to bubbles and rise to the surface while waste rock sinks. In other deposits, acid or alkaline solutions dissolve the target element so it can later be recovered from liquid. These processes depend heavily on metallurgy. Small differences in mineral structure, impurities, or grain size can influence recovery rates dramatically. Engineers must design circuits that respond to the behavior of each specific ore body. A concentrate produced in the processing plant is richer than the original ore. Instead of fractions of a percent metal, the concentrate may contain a much higher proportion of the desired material. Yet even this stage rarely produces the finished product. Further refining usually follows. Copper concentrate travels to smelters and refineries. Lithium concentrate moves into chemical conversion plants. Rare earth concentrates enter separation facilities designed to isolate individual elements. This is where supply chains narrow. Refining requires specialized equipment, chemical expertise, and environmental controls that take years to develop. A country may possess mineral resources, yet still rely on processing capacity elsewhere. So, the processing plant stands as a quiet hinge in the entire system. It is the place where crushed rock begins its transformation into industrial material, bridging the distance between geology below ground and the technologies that depend on these minerals above it. By the time a mineral concentrate leaves the processing plant, the story has already traveled a long distance from the original rock. Yet, the journey is not finished. In many cases, the most delicate and technically demanding steps still lie ahead, because concentrate must be refined into forms that modern industry can actually use. This is where smelters, refineries, and chemical conversion plants enter the picture. In a copper system, concentrate may travel to a smelter, where heat separates metal from sulfur and other elements. The molten copper then moves through refining stages until it becomes nearly pure metal, ready to be drawn into wire, rolled into sheets, or shaped into components that will carry electricity across cities and continents. Lithium follows a different path. Spodumene concentrate or brine-derived compounds must be transformed into lithium chemicals, such as lithium carbonate or lithium hydroxide, materials refined to extremely high purity. These compounds then move onward to battery manufacturers who convert them into cathode materials before the battery cell itself is assembled. Rare earths present perhaps the most intricate journey of all. Mixed concentrates containing many rare earth elements must be separated through long chains of chemical processes that isolate each element individually. The resulting oxides may then be converted into metals, alloys, or magnet materials that eventually appear in motors, turbines, sensors, and defense systems. Refining is therefore more than a finishing step. It is often the narrowest part of the entire supply chain, where technical knowledge, infrastructure, and regulatory acceptance determine who can transform raw material into advanced industrial inputs. That narrowness explains why refining capacity has become a strategic concern. A country may hold large mineral deposits and still depend on other regions to complete the chemical or metallurgical conversion that turns those resources into usable material. In this sense, refining is the moment where geology finally becomes industry. The rock that once rested quietly in the earth has now been drilled, blasted, crushed, separated, and purified through layers of human effort. What remains is a refined substance capable of entering the machines, networks, and technologies that shape the modern world. The mineral has completed its transformation from buried concentration into industrial capability. Once materials reach this stage, they begin to flow through a web of global manufacturing. Refined metals and chemicals leave smelters and processing plants and move into factories where they are shaped into components that may travel through several additional stages before reaching their final purpose. Copper becomes wire and cable. Lithium compounds become part of cathode materials that will later be assembled into battery cells. Rare earth metals become alloys that are pressed and magnetized into powerful permanent magnets used in motors and turbines. These transformations may occur across several countries. A mineral mined in one region may be refined in another, converted into components somewhere else, and finally assembled into finished products thousands of kilometers from the original deposit. The supply chain, therefore, stretches across continents. Ships carry concentrates and refined materials through major ports. Railways and trucks move them inland toward industrial centers. Processing plants, chemical facilities, and manufacturing hubs form a complex network linking geology to technology. Each stage adds value and specialization. The mine produces raw material, but downstream facilities add the precision required for advanced applications. A battery manufacturer does not simply need lithium somewhere in the world. It needs lithium compounds with tightly controlled purity, particle structure, and consistency. This layered system creates both strength and vulnerability. Global supply chains allow materials to flow efficiently toward the industries that need them most. But they also depend on coordination, political stability, and the smooth functioning of transportation routes. When one link slows or fails, the effects ripple outward. Factories may delay production, inventories tighten, and governments begin to examine how dependent their industries have become on distant parts of the chain. For decades, these networks expanded quietly. Industrial specialization encouraged efficiency, and the global economy grew comfortable with supply systems that stretched across oceans and borders. Only recently has the full structure of this network become widely visible. As demand for energy technologies and advanced electronics rises, the materials that enable them have drawn new attention. The quiet industrial chain connecting mines, refineries, factories, and finished products has begun to look less like background infrastructure and more like a strategic system that must be understood carefully. This growing awareness has changed the way governments think about minerals. For much of the modern industrial era, raw materials were treated primarily as commodities that moved through markets according to price and availability. Companies sought efficiency, investors studied cost curves, and trade routes carried materials to wherever manufacturing demand was strongest. Critical minerals have introduced a different perspective. Because certain materials are difficult to substitute and slow to develop, interruptions in supply can affect industries that governments consider essential. Electricity networks, advanced manufacturing, transportation systems, and defense technologies may all depend on materials that originate in a small number of places. That concentration creates strategic questions. If a nation depends heavily on external suppliers for a material required in its infrastructure or security systems, policymakers begin to ask how resilient that supply might be during periods of tension or disruption. The answer is rarely simple. Mining projects take many years to develop, often requiring large capital investment, environmental permitting, and community support before construction even begins. Refining plants demand technical expertise and regulatory approval that may also take years to establish. This means supply cannot be expanded overnight. When demand rises rapidly, the world must rely on existing mines and processing capacity, while new projects slowly advance through exploration, engineering, financing, and construction. Governments therefore look for ways to strengthen resilience. Some countries maintain strategic stockpiles of certain materials. Others support domestic exploration and processing, encourage recycling technologies, or develop partnerships with allied nations that hold important mineral resources. The goal is rarely complete independence. Instead, the aim is balance, ensuring that supply chains remain diverse enough to withstand shocks without collapsing under pressure. In this way, critical minerals move beyond geology and economics. They become part of national strategy, linking earth science with diplomacy, industrial policy, and long-term planning. Beneath the surface of modern technology lies a quieter layer of resource management, where nations consider how the materials of the earth shape the stability of the systems they rely upon. While governments focus on security and resilience, another set of questions unfolds around environmental and social responsibility. Mining and refining are intensive activities that reshape landscapes and require careful management of water, energy, and waste. Every deposit exists within an ecosystem and often near communities that must live alongside the operation. Responsible development therefore requires planning beyond geology alone. Environmental studies evaluate how water systems, wildlife habitats, and surrounding land may be affected by mining. Engineers design tailings facilities, waste storage areas, and treatment systems intended to reduce risk and protect the environment over the long term. Energy use also matters. Many refining processes rely on heat or chemical reactions that consume large amounts of energy. As the world seeks cleaner energy systems, industries are exploring ways to reduce emissions while maintaining the material supply needed for those same technologies. Community relationships form another essential layer. Mining projects often create jobs, infrastructure, and economic activity in remote regions. At the same time, they must address concerns about land use, environmental protection, and the long-term well-being of local populations. This balance can be difficult. Projects may take years of negotiation and consultation before reaching agreement among companies, governments, and communities. In some cases, concerns lead to redesign or cancellation of projects entirely. These complexities remind us that critical minerals are not abstract resources. They come from real landscapes shaped by ecological systems and human societies. The challenge lies in meeting rising demand for materials while maintaining responsible stewardship of the places where those materials originate. Many researchers and engineers now work on improving these processes. New technologies aim to reduce water consumption, capture emissions, and improve waste management. Recycling and recovery methods seek to extract valuable materials from used batteries and electronics, extending the life of resources already mined. The future of critical minerals will therefore depend not only on new discoveries, it will also depend on how thoughtfully the world manages the environmental and social dimensions of extraction and processing. In the quiet background of modern technology, the landscapes that supply these materials remain part of the story. Recycling offers another path through the critical minerals landscape. While mining will remain essential, recovering materials from existing products can reduce pressure on new deposits and help stabilize supply. Batteries, electronics, and industrial equipment contain valuable metals that can be extracted and reused if the right systems are in place. The idea is simple in principle. Instead of allowing materials to disperse into waste streams, recycling facilities dismantle products and recover metals through mechanical and chemical processes. Lithium, nickel, cobalt, copper, and other materials can sometimes be reclaimed and reintroduced into new manufacturing cycles. Yet, recycling also has limits. Products must reach the end of their useful life before their materials become available again. And some elements are difficult to recover economically. Recycling therefore complements mining rather than replacing it. Still, the approach is gaining attention. As large numbers of batteries and electronic devices eventually reach retirement, they represent a growing secondary source of critical materials. Engineers are developing processes designed to capture as much value as possible from these complex products. Design choices can influence this future. Products built with recycling in mind may allow easier disassembly and material recovery later. Manufacturers increasingly consider how their products will be handled at the end of their life cycle. This creates a circular element within the mineral economy. Materials extracted from the earth may pass through several generations of technology before finally dispersing beyond recovery. Each cycle extends the usefulness of the original resource and reduces the need for additional extraction. In practice, the system will likely combine both approaches. New mines will supply growing industries, while recycling gradually contributes additional material from past production. Together, they form a more flexible supply chain, capable of adapting to changing demand. The concept is not entirely new. Metals such as copper and aluminum have been recycled for decades because they retain their properties even after repeated processing. What is changing is the scale and complexity of the products being recycled. As technology evolves, recycling may become an increasingly important partner to mining. Both processes draw from the same fundamental idea that the materials of the earth remain valuable long after their first use. When we step back from the individual minerals and processes, a broader picture begins to emerge. The modern world often presents itself as digital, fast, and weightless. Yet beneath the software and networks lies a vast material system that begins in the earth and travels through mines, refineries, factories, and transportation networks before reaching the devices and infrastructure people see each day. Critical minerals reveal that hidden structure. They remind us that advanced technologies still depend on physical substances shaped through geological history. Each battery, turbine, transmission line, or satellite carries with it a story that began long before the technology itself existed. That story is written in stone. Ancient geological processes concentrated the elements that humans would later discover and learn to use. Mining and refining transformed those concentrations into industrial materials capable of supporting modern civilization. The journey then continued through manufacturing. Factories turned refined materials into components, engineers assembled them into machines, and global supply chains delivered those machines to cities and industries across the world. In this sense, the digital age remains deeply connected to the physical earth. The devices and systems that seem intangible still rely on metals and minerals drawn from landscapes that may be distant and rarely seen by those who depend on them. Understanding this connection changes perspective. Technology begins to look less like something separate from nature and more like an extension of it, built from the same elements that have always existed in the planet's crust. The quiet story of critical minerals therefore stretches across immense scales of time, from geological processes millions of years old to the rapid rhythms of modern industry. The materials of the earth continue to shape how societies generate energy, build infrastructure, and imagine the future. Even in an age defined by information and connectivity, the foundations remain mineral. The earth beneath our feet still supplies the substances from which modern civilization is built.